Hey everyone, in this vector video, vectors number 3, we're going to cover material from assignments number 66 and 67. That's mostly word problems that I want to look at with you today. So let's take a look at this problem. The first problem is you've got two forces acting on an object. Force 1 um, is, in fact, I'm going to use U's and V's if that's okay. Theta V is 30 degrees, and the magnitude of V is 2,000 newtons. And theta U is negative 45 degrees, and the magnitude of U is 900 newtons. So if we visualize what's going on, we've got 30 degrees with 2,000 newtons acting on this object, and then we've got Earth. Negative 45 degrees, but 900 newtons in this direction. So much more in this direction than this direction. And we want to know what's the result of these two forces acting on this one object. And the answer is we just add the vectors together. So we do V plus U, or we do U plus V, and then our resultant vector is this one. This is what actually happens to the object. The object goes this way. Even though there's a force acting there and a force acting there, our object goes that way. So let's see if we can describe some things about this. This is problem 86 from our textbook. It says, given these two forces, describe the resulting vector and the magnitude of the resulting vector. I'd like to do the component form of R, the magnitude of R, and theta R. Okay? So let's go with our normal setup, and that would be that V equals 2,000 cosine 30 sine 30, and U is 900 cosine negative 45 sine negative 45. Okay, and I want to add these together to get our resultant vector. But before I do, I'm going to need to tidy this up. I've got 2,000. The cosine of 30 is root 3 over 2. The sine of 30 is 1/2. And then I've got 900. The cosine of negative 45 is root 2 over 2. The sine of negative 45 is negative root 2 over 2. Okay, and then distribute. So we end up with 1,000 root 3, comma 1,000, and 450 root 2, comma negative 450 root 2. And when we add these up, our resultant vector could be described 1,000 root 3 plus 450 root 2, comma 1,000 minus 450 root 2. Let's decimalize that. 1,000 square root of 3 plus 450 square root of 2. I get 2368.447. And here, 1,000 minus 450 square root of 2. And I get 363.604. So there's my component form of R. If I want the magnitude of R, I'm going to have to put that stuff in the Pythagorean theorem and take the square root. 2368.477 squared plus 363.604 squared. And when I do that, 2368.477 363.477 squared plus 363.604 squared. Don't forget to take the square root. I clearly made a mistake somewhere, so I have to do it again. 2368.477 squared plus 363.604 squared. And then don't forget to take the square root of that answer. And I get the magnitude of R is 2396.224. And then what about theta R? Well, we said that we would use inverse tangent on this component form. Tangent inverse 363.604 divided by 2368.477. So inverse tangent 363.604 divided by 2368.477. And I get that theta R equals 8.728 degrees. All right. And in my mind, these numbers make sense. I'm going over a lot and up a little. Therefore, my angle is going to be really small. And I've got an angle, a magnitude that's bigger than either of the original vectors. And when we sketched our original, and we said, looks like this, Earth. Let's try that again. 30 degrees, 2000, 30 degrees, 2000, and this is negative 45 for 900. And here's our resultant vector. And what we're saying is that this angle is 8.728, and we're saying that this magnitude is 2396.224. Okay, now that's one way to do the problem, and I like that way of doing the problem, and I'd encourage that way to do the problem. Sometimes our book asks us to consider this problem with law of cosines. So let's take a look at this problem with law of cosines and see what you think. Okay, so we had 2000 was the magnitude here, and 30 degrees, and we had negative 45 for 900. And we sketched a resultant vector. We sketched u plus v. We sketched, v plus u. We sketch u plus v. And we end up with this resultant vector, r. And what I'm going to say is I can find the magnitude of r by using the magnitude of v, the magnitude of u, and this angle. Now, how big is that angle? Well, from here to here is 30, and from here to here is negative 45. That's a total of 75 degrees. These are always supplementary, so this is 105 degrees. And so, using the law of cosines, your book loves using the law of cosines here, I can say that the magnitude of r squared is 900 squared plus 2000 squared minus 2 times 900 times 2000 cosine 105. All right, well, let's see what that is. We've got 900 squared plus 2000 squared minus 2 times 900 times 2000 times cosine 105. Don't forget to take the square root of that number, and I end up with something remarkably similar. I'm only off by the rounding error because here I didn't round numbers, and when I did it last time I rounded to 3 decimal places. So these numbers turn out to be 195 magnitude of r. These numbers are certainly the same to the decimal point, and if I hadn't rounded in the first problem, I would have gotten them right to 3 decimal points. So look, I can use the law of cosines to help me find this resultant vector. However, even though the book really likes using law of cosines here, I mean, it's pretty straightforward, I don't because of problem 88 in the textbook. Let's take a look at problem 88. Problem 88 says if you've got 3 forces acting on an object, one is, let's call them magnitude of V, magnitude of U, magnitude of W. This one is 70, this one is 100, and this one is 125. And these are all in pounds. Pounds of force. And we know that theta V equals 30 degrees and theta U equals 45 degrees and theta W equals 120 degrees. Well, the thing about this is I can't use law of cosines directly because I've got 3 sides and the resultant vector would be some kind of strange 4th side, right? But what I can do is I can use my tried and true V equals 70 cosine 30 sine 30 and U equals 100 cosine 45 sine 45 and W equals 125 cosine 120 sine 120. So let's figure out what those are. Cosine of 30, root 3 over 2. Sine of 30, 1/2. Cosine of 45 is root 2 over 2, so is the sine. That's 100. And then 125 times cosine of 120 is negative 1/2. Sine of 120 is root 3 over 2. Okay, so I can then distribute. And now I'm going to have 35 root 3, comma 35. I'm going to have 50 root 2, comma 50 root 2. And I'm going to have negative 67.5 plus 67.5 root 3. And we want to add all these x components together, and we want to add all the y components together. And so I guess I could write r this way. 35 root 3 plus 50 root 2 minus 67.5, and comma, 35 plus 50 root 2 plus 67.5 root 3. Okay, and if I decimalize that, I get 35 square root of 3, close parentheses, plus 50 square root of 2, close parentheses, minus 67.5, and I get 63.832. Over here, 35 plus 50 square root of 2, close parentheses, plus 67.5 square root of 3, close parentheses. 222.624. Okay, so there's my component form of r. The magnitude of r is what I get when I use Pythagorean theorem here. 63.832 squared plus 222.624 squared. Don't forget to take the square root of that. And I get 231.594. And finally, theta r is going to be inverse tangent of 222.624 divided by 63.832. And that gives me 74.001 degrees. Nice. Now, let's think about what's going on here. I mean, we can describe this resultant vector, but we've got these three forces acting on this object, right? One of them is 30 degrees. And how many pounds was that? That was, I used the wrong numbers. Okay, 70, 100, and 125. So this is 70. And then I've got this force at 45 degrees with 100 pounds. And then we had this other force over here, 125 pounds, and that was 120 degrees. And so we've got these three forces acting on this one point. What happens to that one point? Well, what we determined was that it would go off at approximately 71 degrees. This would be the direction that it would go off in. There's our resultant force headed off that way, with theta r equals 71 degrees. I can't do this kind of problem with more than two forces using law of cosines. Side angle side with law of cosines is only going to work with two forces. I could do a much more complicated approach with law of cosines, but why bother? This is pretty easy and straightforward, so I would recommend just adding up these component forms to find our r. We can add up the component forms for as many forces you want working on that one object, and we'll be able to describe where it goes. Okay, the last problem I want to look at with you is one that came to me while I was rock climbing. I used to rock climb quite a bit and before I did Taekwondo, and one of the things that it became very important to do when you're on the side of a cliff a couple hundred feet off the ground is that you build an anchor for yourself to hang on that is not going to go anywhere, because who wants to fall all that distance? So you want to build a really, really strong anchor. Well, so let's take a look at anchors. Let's imagine that we have this point here and this point here. And let's imagine we pre-equalize our anchor so that this angle here is 60 degrees, and this one here is 60 degrees, and this is 200 pounds hanging off that anchor. And what I want to know is how much tension or force is on each of these parts of the anchor. Okay? So let's think about this. Since these angles are the same, I know from the isosceles triangle theorem that these magnitudes must be the same. So the force for this one and the force for this one, they're going to be the same amount of force because these angles are the same. If the angles were different, I'd have different forces on each, and that's a harder problem. Let's save that for honors trig class. For our trig class, we can do this. Now, I'd actually like to rotate this picture 90 degrees because I think it makes the problem a lot easier. So here's my new picture. There's the climber, 200 pounds, going And this is going down, so I'm going to say negative 200 pounds. Negative 200 goes that way. And then we have our anchor, and we have this axis of symmetry in the anchor. We said that this was 60 degrees and 60 degrees, so this must be 30. And this one goes below the x-axis, so I'm going to call that negative 30. Okay, what I determined was these forces would be the same, so the magnitude of F1 and the magnitude of F2 are going to be equal to each other. So I think since the magnitude of F1 equals the magnitude of F2, I'm just going to write that as the magnitude of the force. Okay? And here's what I know. I can write, just like we did in the last two problems, I can describe this vector as the magnitude of F cosine 30 sine 30. And I can describe this one, because the forces are the same, as the magnitude of F cosine, now we've got negative 30, and sine of negative 30. And what I know is, I even know some stuff about the resultant vector. I know that the magnitude of the resultant vector is 200 going down, and I even know the direction angle, right? In this picture, that's my angle for R, so theta R equals 180 degrees. Okay, so let's see what we can do here. First of all, here's sine of 30 and here's sine of negative 30. When I multiply force 1 times this and force 1 times this, these are going to be the same amount in opposite directions. And so when I add these together, here, we'll just write it out. I'm going to get 0, just heads up. So magnitude of F cosine 30 is root 3 over 2. Sine 30 equals 1/2. Magnitude of F cosine of 30 equals negative 30 equals root 3 over 2. But sine of negative 30 is negative 1/2. And so if I were adding these things together, or distributing, I would have magnitude of F root 3 over 2 plus magnitude of F root 3 over 2, comma, magnitude of F times 1/2 plus magnitude of F earth times negative 1/2. Well, this and this are opposites, they cancel, and so I'm just left with 0 there. Over here, I've got one of these things plus one of these things, which makes 2 magnitude of F root 3 over 2, and I can cancel. Okay, so there's my resultant force. But wait, we also know stuff about the resultant force. Theta R is going off at 180 degrees, and the magnitude of R is that 200 pounds. So we could write 200 cosine 180 sine 180. In fact, I want negative 200 here because I'm headed down. Cosine of 180 is negative 1, sine of 180 is 0. I distribute that negative 200, and I get 200, comma, 0. Well, the 0 parts are fine, but I know that's the result, and that's the result. And so I can set those two results equal to each other. Root 3 times the magnitude of F equals 200. So the magnitude of F equals 200 divided by root 3. 200 divided by square root of 3. And I get 115.47 pounds on each. Okay. What if, and that's nice, I think that's less than the climber's weight on each of those legs. Well, what happens if we go back to this problem? Now that we know that tension, We said originally we would have 60-degree angles here, and we would make this nice equilateral triangle, and so this would be 115 pounds, this would be 115 pounds, and that would hold the 200-pound climber safely. 200 pounds. Okay. Now, what if we change these angles? We're pre-building this anchor. We're pre-equalizing it. What if we change those angles instead of 60 degrees to be 30 degrees? We still have a 200-pound climber here. We still know that these tensions or forces are going to be the same. Well, is the tension going to be the same 115 pounds when this angle changes? Let's find out. Okay, so we rotate the picture again. This is 30 degrees, 30 degrees. This must be negative 60 and positive 60. And this is still 180 to our negative 200 pounds. So now I've got tension, tension. All right, I guess we were calling the magnitude of F, but I really don't want to write the magnitude of F and the magnitude of F. So I'm going to say magnitude of F, cosine 60, sine 60, magnitude of F, cosine negative 60, sine negative 60. And I end up with cosine of 60 is 1/2. So I have 1/2 magnitude of F, comma, root 3/2 magnitude of F. And then the other side of the anchor, this times this, the cosine of negative 60 is also 1/2. And the sine of 60 is negative, the sine of negative 60 is negative root 3/2 magnitude of F. And we can see that when we add these together, 1/2 plus 1/2 is magnitude of F. And over here, these are opposites, so they cancel, we get 0. And remember, this was equal to negative 200 cosine 180 sine 180. Well, that was negative 1 or 200. And this was 0. So the 0 and the 0, they're not doing anything. But look what I see. The magnitude of F is now 200. By changing this angle, by making this angle smaller, the force here is now bigger. Now, each of these sides of the anchor has to independently hold 200 pounds just to hold the 200-pound climber. Yikes! Well, what if we made that angle even smaller? What if we made those angles 10 degrees? So this is 10 and 10, and we still have a 200-pound climber here. Okay, so what's that going to look like when we redraw it? If this is 10, then this is 80 and negative 80. And this is still 180 for our negative 200. Okay, so we've got magnitude of F, cosine 80, sine 80, magnitude of F, cosine negative 80, sine negative 80. And what I notice is, again, these are going to be opposites, same amount in opposite directions, so they're going to cancel and I get 0. And here, this cosine value, the overness for 80 and the overness for negative 80 are the same. And so I end up with 2 times magnitude of F cosine 80. And that equals, remember, because we've done it twice now, our component form was 200, 0. So what I know is that 200 should equal 2 times cosine 80 times magnitude of F. And if I'm looking to get the magnitude of f alone, I have to divide by both sides by 2 and by cosine 80. Well, let's see what happens when we do that. 200 divided by 2 is 100 divided by cosine of 80. And now it turns out that when this is only 10 degrees, each of these is taking a whopping 575.878 pounds. 877 pounds. More than twice the load of the climber is on each of these. 575.877 pounds. More than twice the weight of the climber is on each of these simply because of these angles. And so, what we have here actually has a name. This is called the American Death Triangle. You can Google it if you'd like to see. The American Death Triangle says you really will get into huge trouble if you make these angles small. You want these angles bigger than 30, because at 30 degrees, then each of them is carrying the weight on that point. But if you make them smaller than 30, then you get a force multiplier going on, and these things could get torn right out of the rock wall and you could fall to your death. In fact, some people have. So please, when you start climbing and building your own anchors, think about the American Death Triangle. All right, so that's what I wanted to say about word problems today. In our next video, I'm going to go over assignment number 67, the vector review worksheet. I'll see you there.